All right, and so this is now another style of doing trig substitution. Okay, so we have seen from the very beginning of our trig substitution study that we can substitute our variable for an a times sine of theta. And then right before this we learned about how we can substitute our main variable, or our simple expression of the main variable, a variable expression as an a times a tangent theta. So let me introduce another problem right here where it promotes into another style of doing trig substitution right here. So at this point, trig substitutions, there are about two or three different ways of that. Actually, there are a little more in that, but within our standard course right here, we only need to learn those three right here. Okay, and so now I'm going to introduce this problem. Let's evaluate. Okay. Let's evaluate. How about in my promoting problem here? Let's look at how about it's an integral for x squared minus 9. Okay, so it's this integral over here, x squared minus 9. Be careful. Anytime I teach this class, okay, and when it comes to trig substitution, I keep having students mistakenly being mistaken between the two right here. Now, if it's square root of 9 minus x, that's where we are using, well, this 9 here is 3 squared. Okay, then that's where we are going with x equals 3 times sine theta, as we have learned prior to this point. But this here is not quite, the same as this. Notice how subtraction is not commutative. So x squared minus 9 is not the same as 9 minus x squared. As a matter of fact, it's the opposite. And so in that way, surprisingly and shockingly, we need to use a completely brand new way of using the substitution. Of using the trig substitution. But in the end, any of the trig substitution we learn here is an extended style of doing substitution methods right here. Okay, and so here's how I'm seeing it again. I notice that the x squared minus 9, specifically that 9 right here, is the same as, can be thought of as 3 squared. See, 9 here is thought of as 3 squared. So there's an a right there. So now here's, in this problem, allow me to just get straight into the point, and then I'm going to, again, just like any other cases, I'm going to introduce the generality after we're done with this promoting example, this promoting problem right there. Okay, so this is my a being square, because 9 here is recognized as a square, the square of some number. So here I'm going to write my variable x here as 3 times secant theta. Okay, so secant is another style, is another way of using a trig substitution. So for now, up to this point, you have learned 3 different ways. So we learned about substituting our variable with sine theta, and then we learned to substitute our variable with tangent theta, and now we learn to substitute the variable with the secant of theta. Okay, and so as I'm saying, that these are not the only 3, but these are common enough, and then the other ones, the other trig substitutions will come out, once you build your foundation on these 3 right here, you can explore your own on the other trig substitutions. Okay, so now if x equals 3 times secant theta, and again, that same generality, I want to define this under the requirements that the theta has to be anywhere, an angle anywhere from minus pi over 2 to pi over 2, positive. Okay, and then consequently, I have to produce, it has to be equivalent to saying that x over 3 equals secant of theta. Okay, that's one thing we know. And then further consequence, if x equals 3 times secant theta, then the derivative of this function, because right now x, in the way we're writing x, is a function of theta. So just like that same exact fundamental we have seen throughout since the beginning up until now, since the beginning of the trig substitution. And up to this point, it should be trig substitutions. Okay, so there are multiple ways of how to do this. So dx over theta, dx over d theta, the derivative of x as a function of theta, is 3 times derivative for secant is secant of theta times tangent of theta. Okay, and that's how, and I have reminded this multiple times, we can now see this notation here as a ratio of two differentials dx over d theta. So that means I can multiply this d theta expression to the other side of my derivative here, of my equation here. So now I'm going to produce dx equal 3 secant theta times tangent theta times d theta. All right, times d theta. Okay, so now we have had, again, at this point we have had in all the pieces we need to get our substitution started. Okay, so now I'm going to bring all of these substitution pieces into my problem right here and start substituting out. So again, just like that, the square root, the integral sign is the start. The square inside of my square root expression, x is being substituted by 3 times secant of theta. So x squared will give me 9 times secant squared of theta. Okay, and minus 9. That's the other part of the square root expression. And dx now can be substituted by 3 times secant of theta times tangent of theta, d theta. So now I'm looking at 3 times secant theta times tangent theta. Okay, times now I'm running short of space a little bit, so allow me to write the d theta kind of like a jump down to the bottom a little bit. Okay, and so now, just again, it's always in the end, trig substitution, you got to nail it down again. It's an extended version of the substitution method in general. Okay, it's exactly the same kind of problem. So you always have to keep in mind that fundamental. I've taught in the earlier days when we first started to know the substitution method. You got to ask yourself this question: have I completely washed away the old variable? Meaning the x variable was the old variable. Have I completely washed that away? Yes, I have, because nowhere in this current integral here has the x variable any longer, including the d expression here. It's all completely in terms of theta now. So now that means we did our complete substitution. Okay, and so now let's move on. So once we do our problem, our substitution, and now in the next step, as to proceed right here, I can have that common factor, that coefficient here as a factor to be pulled out in front, and this common factor 9 inside of my square root, that can also be factored out. So now I have 3 times the integral. Now inside of my square root right here, I have 9 factored out, and then secant square of theta minus 1. Okay, and then I have times secant theta times tangent theta. Okay, and with a d theta. Okay, and so now in the next step, I am also algebraically going to bring that 9 outside of my square root and to become 3, and as a matter of fact, it will eventually become another 3 multiplied with this current 3 here. So all together, the next step here is going to have a 9, because like I said, that's become a 3 when we're pulling it out of the square root, and then we can also further pulling it out from in front of the integral sign, multiply together with this 3. And so 9 times the integral, but we have square root of secant square theta minus 1 times secant theta. This part here is completely outside of the square root, times tangent theta times d theta. Okay, so now things is getting short quickly. Okay, things is being simplified quickly right here. So I don't need to run to my other board yet, to jump over to my other board yet. So now, as a reminder, see that constant, that identity I've been showing in throughout the earlier case, like the tangent square of theta plus 1 equals secant. It's all due to that Pythagorean identity. So now that means if we're subtracting the 1 from both sides right here, then we're looking at tangent square can be re-expressed as tangent square can equal to secant square minus 1. But hey, how is this useful to our understanding? Secant square minus 1. Secant square minus 1. So that means in my next step, I can substitute secant square theta minus 1 in my square root here with tangent square. Okay, so let's take that and move on to my next board right there. All right, and so on this board right here, on this space of mine right here, we're looking at 9 times the integral, but as I said earlier when I was still on the other board, so the secant square of theta minus 1 now can be written as tangent square of theta. Okay, and then so the expression inside the square root became tremendously shortened and simplified, and now I still have that secant of theta, okay, times tangent of theta, okay, with the d theta here. All right, and so now square root of a tangent square will give me, so here I'm looking at a tangent. So square root of tangent square is a tangent, and multiply together with that other tangent that was already there. Now I'm looking at a tangent square of theta, okay, times a secant of theta. Okay, a tangent square times a secant of theta. All right, and so in this case right here, now when it gets to this problem, it's a trig integral. It's a trig integral. We completely brought our problem down to a trig integral where it involves a two. I mean, throughout the whole lesson here, it's all about the trig integrals, but there are different styles to handle. So for this particular trig integrals, I am going to split this tangent square, again, famously known as secant square minus 1. Right here, tangent square can always be substituted with secant square minus 1 because they are equal. Okay, and so in that way, tangent square, I'm going to rewrite that as secant square minus 1, secant square of theta minus 1, okay, and times an additional secant of theta. Okay, or I should have written that here, 9 times secant square of theta minus 1 times the secant square, times the secant of theta with a d theta. Okay, and I want to save this space for the next step. So in my next step here it's 9, and now I'm going to produce. So from that step right here, in the next step I am going to distribute that secant theta into these two terms. So I'm going to produce a two terms integral. The first term here is a secant cube of theta and minus secant of theta. Okay, all right, and then with a d theta. And that means now I'm going to have an integral with multiple terms where they're all in the forms of powers. These multiple terms are all powers of the secant function, So in this style, I am going to be using the reduction formula. Okay, the reduction formula. But first I'm going to rewrite this as 9 times secant cube of theta, and then minus 9 times the integral on secant of theta, okay, d theta. I'm going to write this a little smaller so I can fit enough in here. So 9 times the integral of secant cube theta, and then minus 9 times the integral of secant theta with the d theta. The d theta. Okay, so two separate integrals, and so we can, once again, I am going to use in that experience I introduced back in the days we learned about even though we might not have a direct video about the powers of secants, but it works similarly when we have multiple terms where they're all powers of secants right there. Okay, then, or you can also learn that generality from earlier part of the lesson here, but I'm going to choose the higher one first, the term here with the higher one, and I'm going to apply the reduction formula, the power reduction formula. And of course we can, and then when it breaks down, and we're going to combine as a like term with the other lower power of the secants here. Okay, so let's get started with that secant cube of theta right here. So secant cube of theta, so here as again, the plan is I'm going to be using the power reduction formula. So now let me remind everyone about the reduction formula for a secant. All right, so here we go, the reduction formula for secant. So the integral of secant to a power n right here. Okay, and that can be equal to all of this right here, that setting. Okay, and then maybe if I'm just simply clearing out all of that and this is the part where we need to pay attention to. The part of that deals with that relates to the power of n right there. Okay, so those are the one that I can extract out to catch your attention. Okay, so now here in my problem, here's how I'm doing it. So our n here in this case, and again as the plan here is saying, it's indicating I'm going to be using the power reduction formula. So power 3 here, so that means I'm going to look at the 1 over 2, okay, because it's 1 over n minus 1. So this is n minus 1 times secant of n minus 2. Okay, so it's now just secant theta times tangent theta. Okay, and then I'm going to add further. I'm going to add with, so now n minus 2 over n minus 1. So n minus 2 is 1 over n minus 1 is 2. So it's another 1/2. Okay, another 1/2 to be multiplied, another 1/2 and multiply with the integral secant to the power n minus 2. N was 3, but n minus 2 now is just 1. So it's secant of theta d theta. Okay, so that's how I used the power reduction formula on my secant cube theta. Okay, and then don't forget we still have that lone term, that lone integral term right here, minus 9 times the integral of secant theta d theta. Okay, and so now I am going to, in the next step, but allow me to kind of modify that right here in this step. We can distribute that common factor 9 into each term right here, making it, so now legally supposedly in my next step, because I'm doing this because I'm out of space right here, it's a 9/2 plus 9/2 multiplied with this integral. 9/2 multiplied with that integral. Okay, and so now, by doing that, we no longer need the parentheses. And so now we have two common terms. Okay, and this term is already done with the integral. All right. And so now in my next step, really, let's clean up the terms a little bit. It's a 9/2 here times secant of theta times tangent of theta plus. Now combining like terms on these two. It's just a matter, because they are exactly the same integral. It's just a matter of having different coefficients. Okay, so 9/2 minus 9. 9/2 minus 9 is going to give me, so indeed it's no longer a plus, but now becomes a minus right here. Okay, it's minus 9/2. Because 9/2 minus 9 is going to, so 9 here is an 18 over 2. So 9 over 2 minus 18 over 2 gives us a negative 9 over 2. Okay, and so now with the integral of secant theta, with the d theta. All right, and so now we have seen how to find the indefinite integral for secant theta often enough. Okay, so now I'm not going to give too much explanation anymore. We know by heart at this point that the integral of secant theta is going to be the logarithm of secant theta plus the tangent theta in absolute value. Okay, so now allow me to erase this part right here. Right, so now in my next step, I'm going to have that 9/2 secant theta tangent theta. Okay, and then minus, but 9/2 now is here, but then the antiderivative or the indefinite integral of secant theta is going to be logarithm of in absolute value. Okay, secant theta plus tangent theta. Okay, and then plus c. Plus c. All right, and so now as far as getting the antiderivative done, as far as getting the indefinite integral problem done, we are done. But we can't just stop here. We can't just stop here, leaving our answer in terms of theta, because our problem in the beginning was asking us to find the integral here, to evaluate this integral here in terms of x. All right, so in that case, allow me to, well, I can still be on this board right here. So we're going to have to go back and look at and look a little further into our substitution that we have done earlier. Now let me clear out some of this extra work right here. But so we place things on the triangle again. So now here's my triangle. There's a right angle right there. And so on these two, on these other two vertices, that anywhere of those two, I can put the angle theta, and I chose to put theta there. So we define x to equal, we substitute x by 3 times secant theta. So that means secant theta equals x over 3 as a ratio. So in a triangle, and you have seen this in the earlier the part of the lecture here that I explained multiple times already. Secant of theta is understood as the reciprocal of cosine, but cosine is adjacent over hypotenuse. Cosine is adjacent over hypotenuse. So now secant means we're looking at this is hypotenuse over adjacent, hypotenuse over adjacent, hypotenuse over adjacent. Okay, so that means x is on the hypotenuse, and then 3 has to be the adjacent side if we put theta here. Okay, all right. So now if that's the case right there, so I'm putting 3 here, adjacent. Okay, hypotenuse over adjacent. And so now if that's the case, that's the setup, then this side here, this edge here, the opposite side has to be square root of x squared minus 9, which is the square of 3 right here. But that's for short. Okay, so in this case right here, because our final current final answer involves a tangent theta as well. So we already found the expression for secant, but we also need to derive the expression for tangent. That's why we need to we're on the need to express our triangles, to express our secant on a triangle. Okay, so now that means tangent is opposite over adjacent. So tangent theta is the same as square root of x squared minus 9 divided by 3 right there. Okay, so now with this understanding in mind right there, now I'm ready to get back to my other board and start substituting things in. So 9/2 here, secant of theta is the same as x over, that's x over 3. Okay, and then I can multiply with, so now it's a square root of x squared minus 9, but over 3 again. Okay, that's how I'm substituting in. And so of course at the end we're going to have to do some simplification here, and I'm going to subtract. So here's a 9/2. My natural log expression becomes so secant is an x over 3, and now I'm going to add with the square root of x squared minus 9 over 3 and plus c right there. Okay, so we've had the expression. So now let's simplify the expression, and we're completely done with the step. So let me completely erase this bottom part of my board so that I can have more work to write. So the 3 times 3 here will cancel with that 9 right here. So 9 cancel perfectly with all these. So here I'm looking at together in one fraction, x times square root of x squared minus 9 over 2. Okay, and then minus 9/2. The natural log expression is here. But then here I'm going to, inside of my logarithm, I am going to combine these two terms into one fraction. So I'm looking at x plus the square root of x squared minus 9, okay, all over 3. It's a common factor 3, common denominator 3, so it's I took advantage of that. We're still having that plus c like that. Okay, and then in that way, at this point you have seen this argument many times. Okay, I have a logarithm of a quotient. So I'm going to simplify this down because, as I said, as I have already explained a few times, there are it's about 70% of professors out there who are okay with this final form already. But in case your professor is one among those the 30% who want students, who prefer students to simplify even further, then here's how you can do that. Okay, well, the first term is here, x times square root of x squared minus 9 over 2. I'm going to subtract. Now it's 9/2. But this logarithm here I'm going to write as a natural log of the x plus square root of x squared minus 9. And then distribute the minus 9/2 together at the same time. And so now in my next step it should be plus. Or I shouldn't rush anyone's learning right here. So how about let's do this. Okay, and minus natural log of absolute value of 3, and then plus c. So everything I'm writing in parentheses right now is just the expanded form of that logarithm before the minus 9 coefficient, or minus 9 halves coefficient. Okay, and then now I'm going to go ahead and distribute that minus 9 halves to each term in my parentheses to eventually remove the parentheses. So that's why it became a minus 9 halves here, and then now it's a plus positive 9 halves here. Okay, and then now we no longer need the parentheses. That's really what happens right there. So watch out for those sign changes right there. You know, throughout my years of teaching, I keep seeing calculus students of mine made silly, you know, sign change errors like that. Okay, and so, but now again, in that same argument, this is a constant, so it can also be included together with the other constant. So adding these together will produce another constant for us. I'm not saying it's the same constant here, but just a constant. So now, and I can go with a plus c here, or for careful purpose, we're going to say plus a c1, but it's just a constant, same fundamental. But ladies and gentlemen, this is now our final answer to this problem. Okay, to this problem. All right, and so now we're as far as this promoting example, we are done. We are done finding the answer to that. The answer, and I carefully double checked and triple checked with that answer to ensure that that's the antiderivative we found successfully. So here, what is the generality we saw here? And as I promised earlier, as we are done with this promoting example, then we are going to look at the generality, so that later on when you're on your own, working on your own problem, you should be able to extend, you should be able to start applying and be more flexible on that. Okay, so a good generality, or the good generality that we can see here, so that anytime you see this, it will rings to your it will rings a bell for you, brings to your attention that we should use the secant substitution here, is that your integral problem contains a square root expression. But then unlike the sine case, unlike the case that we go with sine theta, here we go with x squared that comes first, as first term, positive term, x squared and minus an a squared minus a constant term. It's still a difference in your square roots, but it's x squared minus a constant term, and the constant term is being expressed as a square of a number, the square of some other number. Okay, and so, or more generally, we can see that this is a variable expression. Okay, it could be a variable expression, okay, of x, a variable expression, and then minus the constant term. So this is a constant, that's constant. So that's the generality right there. And so anytime we recognize that, then we can let x, if it's just a simple x variable here, then we can let x equals a times secant theta. That's the simple case. Okay, and then if it's a little more challenging, if it's a slightly more complicated case where it's not only a one single variable, but it's more like a variable expression right there, then we're going to take that whole variable expression, substitute that by a times secant theta. Okay, and then get the problem worked out. And again, doing this substitution, we're under that requirement where theta is the angle anywhere from minus pi over 2 to pi over 2. All right, so that's the generality about this kind of problem right here. And be careful that it's not it's not square root of a squared minus x squared, because we've learned this way earlier. Okay, this is where we use x equals a times the sine of theta, but here it's x squared minus a squared in the square root expression. Okay. All right, and so now we are ready for heading out to our third example, where in this example it's all about different experience, how we explore the substitution by x equals a times secant of theta. So let's look at that example number 3 right here. So in our example 3, we want to evaluate. Okay, and so it's all about evaluating different indefinite integrals. Okay, and so part A. Let's look at our problem here being, let me quickly prepare my notes right here. So I'm looking at the integral of x squared times the square root of x squared minus 4 with a dx. Okay, and so there we go. So it's not as straightforward as the one we saw earlier in the promoting example, but here we have, so but it still has that square root expression, and inside of the square root it has, see, this is the part that caught my attention. The whole problem is more in that the whole function that we're trying to find the antiderivative, or we're trying to find the indefinite integral, has more in that, but at least it has this form right here. Okay, it has that form. And so in that way, here's how I see it. This 4 is the same as a 2 square. Okay, so now our expression, so this 4 is being seen as the square of 2. And so now clearly, just like that the strategy that we have learned now. So I'm going to let x here equals 2 secant of theta. Okay, because that's what I recognized about my expression here. And the square root expression here, once again, is only one part of the whole function in our definite integral problem. But at least we can, once we recognize that, then we can start letting x equal secant of theta. Under that requirements, again, in that requirements that theta has to be anywhere from minus pi over 2 to pi over 2. All right, so in that way, I'm looking at consequently, x over 2 must be equal to secant of theta, okay, which will become useful later. And so now, from that substitution point right here, x equals 2 times secant of theta, then our x can be regarded as a function of theta. So dx d theta, as the derivative of our function x in terms of theta, will equal to, so now I'm looking at 2, taking the derivative of secant is going to be secant theta times tangent theta. All right, and so that means now seeing this together with seeing this notation here as a quotient of as a ratio of two differential expressions like that, and I can multiply the dx to the other side. I mean the d theta to the other side. So dx equal 2 secant theta times tangent theta times d theta. Okay, and so now in that way, I am going to have, I'm ready for making my substitution. I'm bringing all these pieces into our beginning problem right here. So what I have now is going to be, it's an integral. X squared can be substituted by, so x equals 2 secant theta. So x squared must be 4 times secant squared of theta. Okay, and then the expression inside the root here, I'm looking at, so see x squared again is a 4 secant squared theta minus 4. Okay, that's inside the root. And now the dx here can be substituted by 2 times secant theta times tangent theta, d theta. Okay, so 2 secant theta times tangent theta. Okay, and then with the d theta, allow me to kind of jump it down the line a little bit. Okay, and so now in that way, in my next step, I can see that I have the 4 and the 2 here. The 4 and the 2 here can be multiplied together and brought out front as one number. So 4 times 2 is an 8. So really it's 8 times the integral of secant square of theta times square root. Now in this, and then in this same step, aside from recognizing these two can be multiplied and placed in front of the integral, I can also factor out that 4. So 4 inside my square root, and then times secant square theta minus 1. Okay, and now I have simply just secant theta times tangent theta, and then multiply with a little d theta here, and allow me to jump it down the line here a little bit. Okay, and then in my next step, again in that famous identity, and I can also pull that 4 outside of the square root, and eventually realizing that to be another constant coefficient, I can multiply that together with that 8. So, and then, but my point now is that the secant square of theta minus 1 can be seen as tangent square. Okay, because the constant reminder, secant square of theta minus 1 equals tangent square. We saw this many times throughout this lecture already. Okay, and so now I'm going to take that understanding and substitute that tangent square of theta for secant square minus 1 here. And then in my next step, I'm also going to pull out the 4 outside of the root and together the multiply with that 8 in front. So that gives me 16 integral of secant square of theta and then times square root of tangent square theta. So my expression keeps getting shorter and shorter, more simplified and further simplified and further simplified. So here's the secant of theta times tangent of theta times the d theta. Okay, so now I'm fitting enough space in my problem, in my board here. Okay, and then and so now in my next step, I can take the square root of that tangent square here, giving it a tangent. So in my next step, really, I'm looking at, and by the way, secant square times secant is a secant cube. So here I'm looking at 16, okay, integral of secant cube theta. And then tangent square after square root is a tangent, and multiply with another tangent here. We have secant cube of theta times tangent square of theta. All right, and then d theta. Okay, and so now that's our, so we come up to a final trig integral right here and ready for some real action right here. So I'm going to move on to my other board space right there to get things done with from starting with this trig integral. Okay. All right, so from my previous step, the 16 is here, secant cube of theta is here, but the tangent square of theta, I'm going to write that as a secant square of theta minus 1 with a d theta. Okay, so all of this here is due to, so again, we had a tangent square in our problem. So in this specific case, for this specific trig integral over here, then I'm turning tangent square into a secant square minus 1. So we did that before in the square root to turn that to turn that into something that's simple, that we can take the square root out, and then once we combine all things together, I apply that trick again to rewrite my tangent square as a secant square minus 1 like that. Okay. And so keep referring back to my video lecture on how to find integral on trig functions, so that you can recall for yourself those experiences. Okay, and so now with this secant square right here, I am going to multiply the secant cube with each term right there and making it a 2 terms integral. So now I can write this at, let's see, I have enough space. So 16 times the integral, and now I have secant to the 5th power of theta, okay, minus secant cube of theta, and now with a d theta. Okay, so that's my integral so far. So now this is just like how I have done that, very similar to how I have done that back in the promoting example, and you have seen that many times enough throughout this learning quarter, even and including those times where I first introduced the kind of trig integrals with secants. So this thing here has, this integral here has 2 terms or multiple terms, all powers of secant, okay, and so see, power 5 of secants, and the next term is power 3 of secants. That we can be having more, but the point is they're all powers of secants. Okay, so now I am going to apply the reduction formula, the power reduction formula, and I start out, it's just me as a rule, I set out for myself as a rule, I start out with the highest power. I'm leaving that one there the same for now. I'm starting out applying the reduction power, the power reduction formula on the highest power first. So that means to get things prepared for that, I'm going to split my problem into 2 separate integrals. There's a 16 integral of secant to the 5th theta, and then there's another one, 16 integral of secant cube of theta, d theta. Okay, and so that's what my plan is. So now this is n equals 5. If I'm about to use the power reduction formula on this, then I have to understand, we have to understand that the power n here is currently 5. Okay, so one more reminder about the power reduction formula for secant right here. So if we're integrating, if we're taking the antiderivative or the indefinite integral for secant to the n, okay, of x, so n in our case equals 5, then this is the formula right here. So once again, pause the video to take notes if you have to. Okay, and now I'm going to use that in my problem. So now I'm going to produce a pair of parentheses. So now I'm looking at secant cube of theta because it's n minus 2. okay, times tangent. And actually, I already forgot the coefficient. So let me erase it and put it in properly or appropriately. So n equals 5. So the formula says we need 1 over n minus 1. So it's going to be n minus 1 is a 4. So 1/4 secant cube, because n minus 5 after we, in the first term of the reduction formula, and then times a tangent of theta. Okay, tangent of theta. And then I'm going to subtract. So everything I'm doing here in one big pair of parentheses is just for that antiderivative, just for that indefinite integral. I'm still isolating out that coefficient 16 right there. And so now I'm looking at n minus 2 over n minus 1. So n minus 2 is going to be a 3 over 4, because n minus 1 is a 4. Okay, and then here I have an integral, the integral of secant cube now, of theta d theta. Okay, because it's n minus 2 here according to our formula. And then so all of that here in the parentheses is just what happens after I apply the power of reduction formula on the integral of secant to the 5th. Okay, that's what we have all this here in the parentheses. And then don't forget, we still have that minus 16 integral of secant cube theta d theta. Okay, and so in my next step, allow me to stay in this same line right here, but modified to take out parentheses with the 16 properly distributed in. So we still need to distribute that 16 for each term right there. So I'm going to do this cheating step right here instead of writing that as a new step, but I'm short of space, so I'm going to multiply the 16 to the first term, and it's a positive sign with the 16, so there's no worry about sign change or anything like that. 16 times 1/4 will give me 4. 16 times negative 3/4 will give me a minus 12 altogether. 16 times 3/4. Okay, see, 16 cancel with 4 is a 4. 4 times 3 is a 12. That's to quickly clarify that, but it's still a minus sign, came originally. And then from here, and then at this point, I can remove that completely, the pair of parentheses. So now it is clear that we have two like terms. And it's just a matter of combining their coefficients here. So now in my next step, I'm looking at 4 secant cube of theta times tangent theta. Okay, minus, so a minus 12, and then a 12 and a 16 together is a 28, right? So minus 28 integral. And I actually have to correct this. It shouldn't be a minus there from the beginning. So if we roll back from here, it should have been a plus right here. Okay, and so now, so it's a plus, but it's a plus 12. And so here's the thing. Because our formula was a plus, and I mistakenly used a minus there earlier. But then, plus 12 combined like terms with that minus 16 right there gives me a minus 4 here actually. So that does change the coefficients a little bit. Good thing I double checked with my lecture notes right there. Okay, and so go ahead, and if you happen to take note on the step before this, before I distributed that 16 right there, go ahead and correct your sign there in the step right before this as a plus instead of a minus, and even the step before that. Okay. So now I'm going to have minus 4 integral of secant cube theta d theta. Okay, and so now I am going to apply that power reduction formula again on this secant cube theta. So it's 4 secant cube theta tangent theta. The first term here stays the same, minus 4. Okay, and I have to be extremely cautious with my sign this time. Okay, but power n is 3 this time if we are using the power reduction formula. Okay, so power n is 3. And so in this case here, I'm looking at 1 over n minus 1, which is a 1/2. Okay, which is a 1/2 times secant, but n minus 2. So this is secant, just a secant up to the first power. Okay, times tangent. Okay. And just like that mistake, so to avoid that mistake I've made earlier, this is now actually plus, not the minus. So go back to that step where I used the reduction formula, the power reduction formula when it was to the 5th, like that, and correct that. The sign there was supposed to be a plus sign instead of negative. Okay, but now I have a plus here, And my formula says n minus 2 over n minus 1. So n minus 2 is a 1, n minus 1 is a 2, so a 1/2. And I produce for myself another integral. N minus secant of n minus 2. Secant to the n minus 2, which is just secant of theta. Okay, with a d theta. All right, so now that's what I have right now. And then I can go ahead and distribute that minus 4 to each term. See, it's not so long if we know how, I mean, of course it's long, but if we know how to organize our steps to keep things in a certain order like that, then we can keep track of all the little steps, which makes things still somehow manageable. Okay, and so now multiplying that minus 4 for each term right here, then allow me to do this, again, this cheating step right here. Minus 4 times a 1/2 gives me an overall minus 2. Minus 4 times a 1/2 again. Now that sign switched to a negative sign. So now it's become another minus 2 times of that integral on the secant. Okay? And oh boy, we have done that integral of the secant a lot of times up to this point. And so now I'm going to have one quick line right here. So 4 secant cubed of theta, tangent theta, minus 2 times of secant theta, tangent theta. And I'm subtracting 2 times the natural log. So just that, okay, just that integral of the secant theta is a logarithm of, in absolute value, secant theta plus the tangent theta. All right, and then plus c. Don't forget that plus c. So now this is our final antiderivative, our final indefinite integral for that ugly looking expression, but it was completely manageable. Okay, I'm saying ugly looking, I mean it's not really that ugly looking to me, but I'm saying ugly looking as I understand how you feel when you're going through these, but I'm trying to point out in my best capability to show you how you can organize the problem, so to keep it safe, I mean to keep it easier to manage, okay, to keep it more easily manageable for you. Okay, so now once we get to that final antiderivative, final indefinite integral, we can't stop there yet, okay, because we need to once again bring it back to the original variable, which was in terms of x right here. Okay, so now let's look at a couple things here. So we already knew that x is, 2 times secant theta. So consequently we came down to this expression. Okay, and then further, now let's place things on a triangle again. So in our triangle, okay, there's a right angle right there. So aside from that right angle, we can put our angle theta anywhere among the other vertices here. So I put my theta here. So secant equals x over 2. So I've made this argument many times before. So secant is now, secant is the reciprocal of cosine, but cosine is adjacent over hypotenuse. Okay, so the reciprocal, secant is the reciprocal of adjacent over hypotenuse. That means secant here has to be hypotenuse over adjacent. Hypotenuse here, adjacent is here. Hypotenuse over adjacent. So hypotenuse over adjacent, that means x is here and 2 has to be down here. So in that way, my other length right here, opposites from the side that's opposite from the angle theta is going to be, according to Pythagorean theorem, square root of x squared minus 4. Okay, so that means because eventually we have to deal with a lot of tangents. See, our current final answer here for the antiderivative involves a massive amount of tangent right there. Okay, so now in that way, we're going to need to derive a quick understanding for tangent. So here, tangent theta equals, so now we're looking at, see, opposite over adjacent. Okay, so square root of the x squared minus 4 over 2. All right, so that's our tangent theta. Okay, so now with tangent theta, now we have everything we need to put things in places here. So I am going to start erasing. I'm going to erasing from this line and up. Okay, and then if we need to, I'm going to erase some more. All right, so now in this problem, in this current final answer of the indefinite integral, then so 4 times secant cubed theta, but secant of theta, so 4 times secant cubed, but secant of theta is x over 2, so x over 2 cubed. Okay, and tangent of theta we found previously from the other word to be square root of x squared minus 4 over 2, so we found that there. Okay, and then I'm going to subtract, according to the final answer here, 2 times secant theta times tangent theta. So 2 times, okay, and then secant theta is an x over 2 again, okay, and tangent theta is that square root of x squared minus 4 over 2, like that again. Okay, and then 2 times of that logarithm. So now I'm running out of space a little bit, so I have to write it down below here. 2 times, minus 2 times the logarithm of, so now I'm having secant is an x over 2, so maybe I actually have enough space to write on the same line here. So minus 2 times logarithm, and in absolute value secant is an x over 2. Okay, plus, and tangent is the square root of x squared minus 4 over 2. All of that is in absolute value. And then I'm going to need to add to c. We need to add c like that. Okay, and so now we can start doing the cancellation. Okay, simplification work. At least we have successfully expressed our final answer in terms of x here. Okay, and so now x cubed, I mean the x over 2 cubed right here, that gives me an 8. That's multiplied together with that 2 right here. It gives me a 16. Cancel with that 4. So I'm now looking at altogether in one fraction. X cubed square root of x squared minus 4 over, the 4 cancel with the altogether down here is going to be a 4 right there. Okay. All right, and so now minus 2 cancel with that 2, but then there's still that factor of 2 remains. So it's x times square root of x squared minus 4, okay, over 2. That's done with that term, okay. And then now I'm going to subtract 2 times, and then I'm going to, just like the earlier problems we have done multiple times, like that, I'm going to combine these two into one fraction. So 2 times natural log, and now I have x plus square root of x squared minus 4, okay, and in over 2, and then plus c. All right, and now I have left this here long enough, so I'm going to clear out some more to make more space for myself. Okay, and I don't think I need to erase this. All right, so now the first 2 terms are done. So in my next step, I'm going to retain those. X cubed square root of x squared minus 4 over 4. I'm subtracting x square root of x squared minus 4 over 2, and minus, and now I have 2. Now I'm going to write this as a difference of 2 logarithms. So minus 2 times a natural log of x plus square root of x squared minus 4. Okay, that's one of them. Minus, and then the natural log of absolute value of 2. Okay, and after that parentheses, I'm going to plus c right here. I'm going to plus c. Okay, but so in the end, really, it's just I'm going to distribute that minus 2. So minus 2 multiplied with that gives me a minus 2, but minus 2 multiplied with that minus term right there, it's going to make it positive 2. So now really I'm having minus 2 natural log, okay, natural log, but then here it's a plus, okay, plus 2 natural log of absolute value of 2. And so now together, this is a constant, as we have seen, this is a constant, it can be included with that c. So my final answer here comes out to be, now in my next step, allow me to do this cheating again, this cheating work again, but including all that as one constant c. Now I'm going to erase that and turn that into just some c1. Even though if you're writing a plus c, no one can be unhappy with that. Okay, but just for safety, I'll write it as c1 just to make clear that it's a different c value with this. But in the end, it's just a constant. So as I said, if you're writing it as a plus c right here, it's not anything illegal. Okay. All right, so that's now our final answer of how we have found, this is our antiderivative or our final indefinite integral for this problem in the beginning. integral of x squared times square root of x squared minus 4 right there. Okay. All right, and so I have one more problem for us all here in this example 2 over here. So let's look at what that problem is after I erase my board here. All right, so let's now look at part B of our example. So let's look at an integral, and then here we have square root of how about 9x squared minus 4, and then over x. Okay, with the dx expression right there. Okay, and so here's what, here's how I'm seeing. We have a square root expression again. So at this point, since we're coming close to an end of our lecture about all the trig substitutions, it rings a good sign that anytime we saw a square root, it rings a good sign. I'm only saying it rings a good sign. It may high chance it work, but there's still chance it doesn't. But the idea is it rings a good sign let's try a trig substitution, if that can be an option. So right here, let's tackle down with that. Let's understand a little further about our square roots. Even though we don't always have to use trig substitution when we see square roots, but anytime you see square root, it rings a good sign. That's what I'm saying. So now 9x squared minus 4. That's what I see. So here's how I'm seeing the 4 here. It's a 2 square, okay, and then the subtraction sign right here, and then the variable term. It looks like it's not just an x squared, but it's something with the x squared. And so now 9x squared can be seen as a 3x all squared. All right, the 3x all squared. And so now, just like how I pointed this out in the generality right here, as long as we recognize that inside of our square root there's a variable expression here. That variable expression being the 3x. So there's a variable expression square minus the square of a constant right here. Then here we can use our secant substitution. Okay, and so now I pointed out that this problem here has that part where it fits perfectly into that trigger our use of the secant substitution. So now here's how I start. All right, so I'm going to go with the 3x here. I'm going to let 3x to equal 2 secant theta. Okay, 3x to equal 2 secant theta. Again, because this, I see that as a square root of 3x all squared minus 2 squared. That's why. Okay, and so from this substitution right here, then I can see that I can divide both sides by 3 and have x equals 2/3 secant theta. That's one thing. On the other hand, I can also do dividing both sides by 2 right here. Right from that important substitution point, I can also divide both sides by 2. That leads me to 3x over 2 to equal secant of theta. This will become useful later. But now, right here at this point, when I'm having x equals 2/3 of secant theta, then I can proceed to find dx d theta. All right. So dx d theta here is a 2/3 secant theta tangent theta. So I'm a little short at space, so allow me to write it here. Dx d theta, I have to write. Has to equal 2/3 secant theta times tangent theta. Okay, secant theta, tangent theta, and then I'm going to multiply the d theta over, just like that, because we recognize this now not only the derivative symbol, but it's also a quotient, a ratio of two differential expression dx and d theta. So I'm going to multiply d theta to the other side. That leaving me dx equals 2/3 secant theta tangent theta, okay, and with a d theta. All right, with a d theta. So now with all that here, I'm ready to put all these substitution pieces in place right here. Okay. So now I'm looking at the integral. Okay. The x in the denominator here can be written as a 2/3 times secant of theta. So see, x equals 2/3 times secant of theta. So now I'm going to substitute that for the x at the bottom. Just write it down the way it is, 2/3 times secant theta, okay? But then it's a coefficient, so eventually we're going to do some algebra on that. the square root expression gives me, okay, so this is now 3x all squared. So 3x is substituted by 2 secant theta. So that means 9x squared. 3x all squared is going to be 4 secant square theta, and then minus 4. Okay, and that's how I see that in the square root. And then the dx now can be substituted by, that's a 2/3, okay, secant of theta times tangent theta times d theta. Okay, and then there's another good news right here. The 2/3 here will cancel even before we have to do any algebra, any further algebra. It cancels immediately with that. Okay, so now I have already shortened down my problem, so it turns into the square root, right? And actually I didn't leave enough space for my denominator, so there's a secant of theta in the denominator. Okay, and actually allow me to even point out further before I get into that next step. I should have noticed that as well. I should have pointed this out. The secants also cancel with that secant. We can cancel that out. Okay, so now we're actually completely free from the denominator. Okay, so it's a good thing. So now that's a square root, integral of the square root of 4 secant square theta minus 4, and then times tangent of theta d theta. Okay, so the problem now has become significantly reduced. Okay, and so now just like that, I can factor out that common factor of 4 and at the same time pull it out as a square root, making it a 2. 2 times square root of secant square minus 1. But then the 2 here can be placed in front of the integral. So in our next step, see, allow me, as you have had enough majority right here, I'm going to start combining more little steps into one step right here. So now factoring out that 4, and factoring out that 4 and put it in front right here. So it's going to be, and going through the square root is a 2. And now square root of the secant square theta minus 1. Okay, and then times tangent theta with a d theta. Okay, and so now again, just that reminder, secant square theta minus 1 equals tangent. Secant square of theta minus 1 equals, actually I said a little bit slightly incorrectly, equals tangent square, not tangent. So secant square minus 1 equals tangent square. And so now I can substitute that tangent square into my current square root expression. So there I have, so that equals 2 times with the integral, so now square root of tangent square theta, and multiply with a tangent theta, d theta. Okay, so I have, that's what I have there. And now, so now I definitely need the space on my other board right there. All right, so now in my next board space right here, so I am now going to take the square root on that the square root of that tangent square. So square root of tangent square here will become just tangent, and then multiply together with that other tangent outside the square root already. I'm going to be looking at 2 times integral of tangent square theta. All right. So now it's a final trig integral before being ready for finding the final indefinite integral right there. There are a couple options. So you can use a power reduction formula for this as well, because I see a tangent square, okay, a power of a tangent. So in case you are going with the power reduction formula, this is the power reduction formula that we can use right here. So tangent to the n, so n here is going to be 2 in our case, okay, and then these are the places where you gotta know how to use your power right here, and that's what it means by reducing. Okay, so that's for the option of using the power reduction formula to solve our problem, because we're looking at tangent square. Okay, but allow me on this board right here to stay with just the fundamental solving work right here. I mean more direct instead of using formulas, because there could be times where we don't always remember formulas, right? So tangent square can be expressed as, again, we know these identities from trigonometry. Tangent square is secant square of theta minus 1, okay, with a d theta. So that means now I have 2 terms, okay, and then so I'm going to write it as a 2 integral of secant square theta with d theta minus 2 integral of d theta. technically it's a 1 times d theta, a constant 1 times d theta. Okay, and 1 times d theta. So now I'm ready. This one here, I find it easier than using the formula because it makes me keep track of all the end right here. So that's why I chose not to go with the formula, even though it will work and give the exact same result. Okay, so secant square. Isn't this the derivative of tangent? So taking the antiderivative of secant square will give us, so first term here, boom, it gives us 2 tangent of theta. Simple. Okay, so that takes care of the first integral. Now the next integral is simply just, that's a simple integral, power rule here, power 0 of theta. And it's an integral in terms of theta. So 2 theta plus c. So we're done. We're done with taking the antiderivative. Okay, we're done with taking the indefinite integral. However, we can't just stop here because, again, we need to bring back our original variable, which is in terms of x right here. Okay, so now I'm going to need to, again, swing by my other board right there to develop out some further arguments. So now 3x equals to 2 secant theta. And so that means secant theta itself is a ratio 3x over 2. So now think of how we use that famous triangle over here with a right triangle being written somewhere, right? Then anywhere among these 2 other vertices aside from that right angle, then we can place our theta. I chose to put my theta here. Okay, so that means what? Secant is known to be what? The opposite, I mean the reciprocal of cosine. Secant is the reciprocal of cosine, and cosine is adjacent over hypotenuse. So the reciprocal of cosine, meaning the reciprocal of adjacent over hypotenuse, that ratio there. So that means secant now has to be hypotenuse over adjacent. Hypotenuse over adjacent, hypotenuse over adjacent. So that means I put that there in the hypotenuse, and this is adjacent. Okay, and so my opposite here, according to the Pythagorean theorem in a right triangle, here we're looking at 9x squared, because that's the square of the 3x right there, minus 4, the square of the other of the adjacent. So this is my opposite side right here. So I'm going to go ahead and find tangent from this triangle. So tangent is opposite over hypotenuse. I mean opposite over adjacent. So square root of 9x squared minus 4. I'm going to divide it by 2. This is, ladies and gentlemen, tangent of theta right here. But further, now let me remind anyone, we're not, aside from secant and tangent, here we only have tangent, but sadly, we also have theta. Okay, so let's find an expression in terms of x for theta. So there's a couple options. There are a couple options already. We can go directly with secant. I mean, theta can be expressed as a secant inverse of 3x over 2. That's one option. That's one option. Nail that down for me as well. Okay. And then, but then later on, when we get into the actual problem, allow me to show you some alternative way of thinking. But now we have enough pieces of information to put that in place right here. So I'm going to put all of those substitution pieces back right here. So tangent of theta is that. So now I'm looking at 2 times square root of the 9x squared minus 4 over 2. Okay, that's tangent. That's what substitutes for tangent theta. And then the 2 here will eventually cancel. And now I'm going to look at minus 2 times here one version. I'm saying one version, one alternative. I'm using secant inverse of 3x over 2. Okay, plus c, and then canceling out the 2 here. My final expression here is a square root of 9x squared minus 4. Okay, no more fraction, minus 2 times secant inverse, okay, of the 3x over 2 plus c. All right, so that's one version. Okay, that's one version. All right, so what does that mean by one version? Because this is more common. Okay, but for me, it's just me personally, I don't have personal experience. I don't have very good personal experience with secant, especially secant inverse. Okay, so allow me to go this way. So let me take away a little bit of board space right here. Okay, so from our understanding earlier, 3x over 2 being our secant theta. But secant again is the reciprocal of cosine. Secant theta is the reciprocal of cosine. So that means I can, from this, we understand that as, we can rewrite it as cosine of theta is argued as to be equal to 2 over 3x. 2 over 3x. Okay, so 2 over 3x means that theta can also be re-expressed as cosine inverse. So I have better experience with the cosine inverse. So now theta can be also expressed as cosine inverse of 2 over 3x. Okay, and so now with that simple thing right here, my alternative, my own version is everything is exactly the same except for except for a couple of places I changed the secant inverse to cosine inverse. Okay, and instead of 3x over 2, it has to be 2 over 3x, and that's the alternative version that I was talking about. Okay, but that's how we solve this part B of our example 3 right here, and that's really at this point completes all of our understanding regarding the trig substitutions. And at this point, it's trig substitutions. There are multiple ways of using a trig substitution. I introduced 3 in my particular lecture here, but there are more than that, because remember, in the basic family of all the trig functions, we have up to 6 of those. We only use 3. That means we also have a choice of using the other ones. But I want to leave that for users and for viewers and students of mine to explore on your own, because they are closely related to the 3 primary ones that are being introduced here in this lecture. Okay.